Okay. Um, so thanks for joining us again for another coding interview question. Uh, so this time, um, our question is Sean, I want you to implement a function to check if a binary tree is a binary search tree.
Okay. So binary tree is a binary search tree. Okay, so if a binary tree is a tree that well, binary search tree is a binary tree that has a particular order
Mhm.
to it. Do you want to search for greatest or yes?
Well, I want to
Oh,
determine
yeah.
if that tree
It's a binary search
is
tree. Yep.
a binary search tree. So,
Okay.
what would
Yeah.
be what conditions would have to be met?
The root. It doesn't have to be a balanced binary search tree,
No,
right? Okay.
no.
Okay, so for every children in the node, the left one is smaller than the particular node, and the right one is bigger.
Mhm. Um, okay, so
And are we storing integers in these binary search trees?
let's say we're dealing with integers.
Okay.
So actually to expand on your definition of a binary search tree,
Mm-hmm.
uh, but actually, so it's not just that, sorry, what was your definition again?
Every node on the every left children of a node is a
Uh-huh.
number contains a number smaller than the
Okay.
node itself, and every node on the right it's bigger.
So for this case, we're gonna assume that um, no, actually, yeah, sorry, go on. I interrupted you.
Okay. Uh, so what we can do is just an example. We can do like 10.
Mhm.
Uh, so we're given the head, right?
Mhm.
And we're guaranteed is head guaranteed a member or is a valid node that's not null.
Yeah, yeah.
Okay.
Let's say it's not null.
Okay. Um, so for this example, I'm gonna use like 5, 12, 1, 7. This can be like 11, and this can be
Mhm.
15. So this is a binary search tree. Let's see. Okay, and we want to check if it is one, if a tree is one.
Mhm.
Okay, okay. So what I'm thinking, just walking through this, is you have head.
Mhm.
You mark. Hmm, uh, you look at 10. You check if 5 is less than 10.
Mhm.
Put this in a data structure somewhere to save it. You check
Okay.
if 12 is greater than 10. Put that in the data structure and save it. Maybe like a queue, so like you can pop the 5 afterwards. and then you do the same for its children. And the moment you fail, you can return false. Um, so this will be.
So how would that look like?
Sorry.
So okay. Why don't we walk through that?
Okay. Let's see. Let's say this is a queue. So we can initialize by putting 10 inside the queue.
Okay.
And then in like a subfunction which checks the queue, you can pop 10, check check if left is smaller than 10. If that is, push it in the queue. Check if right is bigger than 12. If that is, push it into the queue. And we can pop 5. Do it for 1 and 7. So 1 is yes. 7 is bigger, so that's yes. Pop 12. Do it for 12's children. Do like 11, 15. And then do it for 1. So if it's okay if it doesn't have a children. So you check both. If it's either smaller or no, if the left is smaller or no, or right is bigger or no, then that's a factor. That's a good condition. So there's like no children here. So let's say we put one more children here. 16. So this will have nothing. 15 will have nothing for this. We'll have 16. 15 will pop, and 16 still passes. So once you're done with everything in your queue, since a binary tree is guaranteed to be connected to all the nodes, or at least one connection to all the nodes, we've essentially did a breadth first search on the tree and went through all the nodes.
So what about conditions where you have duplicate elements?
You have to what?
What if you have duplicate elements?
Duplicate elements.
Yeah.
So what we're storing is references to the node here in that sense.
Okay. Mm-hmm.
Yeah, so we don't worry about that. In a binary search tree, if we have duplicate elements,
so that really depends on the definition, right? Because
right.
Some people say for it to be valid, it has to be all unique, and then for some other definitions, one side has to be, or can be greater or equal than.
Right.
Greater or equal. So would that affect? Or no?
Yeah, I think duplicate elements would. Would it?
I'm not saying it will. I'm just trying to see if you thought of it.
Oh, well, now I have thought of it. So should we allow duplicate elements in this binary tree? Not that it really matters, right? When we can define duplicate elements as like, let's just do less than or equal to, and that'll solve that issue.
In our example, we don't allow.
Okay.
So if it has a duplicate element, it's not ABS2.
Okay. So then we can also check.
Would that simplify things?
Yeah, I think that would simplify it. That would still follow, that current algorithm that I proposed would still follow, would check for unique. Because we're only checking for less than here, and then greater than, oops, other way around.
So how much storage would you need?
You'll need n for n nodes for this one.
Could you do it with even less storage?
You could. You could do, so breadth first search requires you to store it. What you can do a depth first search,
Okay, so how would
which doesn't use any storage. It would be using a recursion, so you can do 10. A depth first search, let's say we populate the left first before we go right. So you would say 10, visit 10, check 5, check if it's less than 5, and then recurse on, let's see, visit 5, check if 1 is less than it, it would pop, and then the second line of the 5 would check 7 to see if it's greater than it. And if it's success, pop the 5 and 10. Back in the 10 call, it will check the right and keep going. So, yeah, so you would literally check the right node, get the value of the right node, check if it's valid, and then go to the right node if it is. Or left node, sorry. So we probably have like a condition that's let's see. So I guess the base case for this one is if it's like left equal to null, and right is equal to null. How a depth first search is populated is, I guess, like you take the element itself, just in a very general sense. You take the element, you check the left, recurse on the right, on the left, and then you recurse on the right. So I guess for this ticking, we can just check the left and the right because we kind of have these. So in this tick, we do like check node children valid. And then we just recurse left. So 10 recurse, check is this valid? Yes it is. Now we recurse left. For 5, is children valid? Yes. 1, no children, so we return to 5, and it's the recurse right. 7 has no children. What if I gave it a children? So let's do 9 here. It will go to 7. It'll check that, right, so in this valid we can say if one of them is valid, is null, that's fine. Let's do like, if one is null, that's okay. If one child, sorry.
So in this example, what if that 9 wasn't a 9? What if it was 10?
Right.
Would it be valid? I mean, it wouldn't be valid, right? So how would you deal with that?
So you know, say an example where this is like 6, and that is invalid because it's on the right.
No, let's make it 20.
Okay.
You see why it's invalid.
Oh, I see. Yeah.
So how would you deal with that?
And this is like 19. That's invalid. You can pass. If there's an element on the left, passing the parent itself for the last left parent, for the last right parent. So I guess, so let's see. So if this is 19, we somehow want this 10 here. So we know it can't be greater than 10. Likewise, if 1 was like a 2 here, we want to check if it's 5. So I guess you can say on every left recursion, pass in the number itself and use that as the check for its children. So when 10 goes into 5, you somehow have a reference of 10 into the recursion. So 5 knows 7 can't be greater than that 10. Same with the 1 check with the 5. Likewise, in this case, this could be like, this can be, I guess, 9. So on the right recursion, you pass in the parent right recursion, the last parent of the right recursion, which would be 12.
Well, so what's the definition of, and you actually told me this very early, right? You said that what if the BST basically has to follow a rule where the left subtree of the node has to contain nodes that are all smaller.
Smaller than the parent.
The tree has to be all greater than root 2.
Yep. So I guess I would add another case in there, that is binary search tree. I'm trying to find a better way to explain it.
What if for now I said, uh, is there a way? So, I mean, I want to see you do it without using, or just use constant storage. But then I think to get to there, it might be easier to start with ON storage. Is there, so if you had ON storage, is there a way where you could
Mm-hmm.
check whether it's a BST first and then build on that?
Yep. Let's see. When you say constant storage,
So
yeah.
so not ON storage.
Yeah, I know. Give me some time to think. Um, hmm.
So what kind of traversal are you doing if you're looking at all the, if you're looking at the left nodes and then the right node? What kind of traversal is that?
Well, you look at it for both, right? Depending on where the left node and then the right node, as
So
in per level on or per depth wise.
um okay,
Mm.
so for if a binary tree is a binary search tree, then well those rules apply, right? The ones we talk about. But what does that also mean? Like what is, I mean, if you wanted to explain it in simpler or okay,
Uh,
can you implement a binary search tree using an array? So this isn't, I'm not telling you to do that. I'm asking you,
okay.
yeah, like
You would go
you can.
down. I guess you would balance it from the top,
I'm so
or you would attach it to the bottom and then percolate up. Binary
so
search.
what's the characteristic of, okay, so if I said to represent this binary search tree as an array,
Mm-hmm.
how would you do it?
Um,
Or
I would.
so or rather if you had a sorted array,
Uh-huh. That is right.
um, can you do a binary search on it?
Yes, you can. That is the tree, but just collapsed
Or,
into. Yeah, so you get the halfway mark. Um, and then check if the element's bigger or greater, or less than or equal to, and then you check the left half or the right half depending on your answer. Um, but we are given a node tree structure.
Maybe that wasn't the right thing.
So what if you populate it into an array? Is that what you're saying? No.
So I'm not telling you to do that. I'm just
Okay.
okay. So
Give me a
essentially,
second. Give me a second. Unless you're trying to push this along. Um, I think there's one. I guess there are instances where you can traverse each node and keep like the bounds of each node as you're going down. So as you're going down, the bounds get smaller and smaller. So if you're like 10, if you go to 5, you know 10 is your upper bound.
And then what about,
And
let's
for
say,
5,
okay.
you're going down, 5 is your upper bound. But if 5 is going to 7, then you know 5 is your lower bound for 10, and so forth. So for every left traversal, you change the upper bound, and for every right traversal, you change the lower bound into that element itself. And I think we can do a recursive, like depth first search this way. Yes, yeah. So I think I'm pretty sure we can do it.
Okay, so let's walk through that example.
Okay, so I think when we recurse right, so we have like, we can go like left, pushing the left node, and then say like this is lower bound would be if on the left you're changing the upper bound. So you keep the same lower bound. The new upper bound is the value of the node. And this is like, right, the same, but it's like flip-flopped. So let me just quickly walk through. So we can
For the right part, I think you might want to check the bounds.
if we're going right.
Yeah, the recurse right part. The stuff.
If you're going right, upper bound.
So what would the lower bound be for that?
The lower bound would be the value of the node.
And what would be the upper bound?
The upper bound, the same upper bound of the last iteration, right? Oh, that's this, right? Oh, yeah, I don't know if this is confusing, but I think that might help. Um, yeah, so I think this can work. So our function would take two more arguments, a recursive function, and should I get to coding?
Yeah.
Okay. All right. How are we doing on time? It's like 30, 40
Uh,
minutes, 45?
so you've been doing it for 28 minutes.
Okay.
So that's some timelines.
Let's do. Check for biggest T. So we're assuming we have node, I guess, head. It's the tree structure. We're guaranteed that this is a binary tree, right?
Uh,
So we don't have to
so
do like children checking.
oh no, yeah. It is a
Okay.
binary tree.
Okay. So um so then we can do mm, I'm not sure what I want to put in for head. Why do I do
Well,
this? Is this legal, Greg?
I have never seen that before. So
I'm not sure this is a Java syntax, but in C# you can have a nullable type.
mhm.
It's basically saying if something is null, then like an integer can be null. Like this will need to be an object if that's the case.
Why don't you use an integer rather than int? That way, because you want to set it to null. Is that what you want to do?
Right.
So yeah.
Let's do something. I'm pretty sure this is the syntax, but,
No,
we'll just assume for now.
I mean you don't need this. Your
Oh, right. Yeah, you're right. So when we have no, that means we have no restrictions on it, such as we're traversing
yeah,
down one side of the tree.
yeah.
Um. Okay. How do I want to do this? Okay, the base case. This base case would be if the null is just a children, I guess, the last leaf in the tree. If node dot left goes to null
Mhm.
and node dot right goes to null, then we know we're like done with this def, and we should just return something. I'll figure that out later. Um, So now we check the node itself if it's valid. I'm gonna abstract this and say check left node node.value, and then do lower upper, and then I'm gonna do check right node node.value, lower and upper. So that ideally would take care of the tick here, this portion. Now we do recurse. Let's do recursion check. We want to go left first. Doesn't really matter, but we're going left first. Node.left. Do we need to check if it exists? Why don't I just check if the node itself exists? I think that's a little bit cleaner.
Okay.
If the node itself exists, then we need to check the children for this. So I guess inside check left node would just pass children. So let's just do left, right, and then we do a recursion on the left. So the lower bound, as stated here, is the same as the last one. So the lower, but the upper bound would be itself. So node.value. And then we do another recursion check node.right. Let's do this would be the value itself, and then the upper here. So we really want to return a boolean. Is that correct?
Yeah.
For the tree, check. So this should be boolean. So if the recursion check we can say I guess a left valid is equal to, this will return if the left is valid. This is right valid. We can't return this right away because we'll miss the recursion. So we can do return valid and right valid. If null is equal to, just return true. Okay, so Would you like me to implement the recursion check itself?
Yep.
Or sorry, the check left node and check right node?
Yep.
Okay.
I want to see it working, so
Sure.
I'll see that.
Okay, I think I can combine these two together. Um, yeah, why don't yeah, just do check node here.
Okay.
And then we check it itself. Let's do like this valid. So let's do oh, it's really laggy for me, is it? For you? Yeah, it's like
Oh, yeah, I didn't see the typos. Okay,
Alright.
so I'll just look that for
it might be yeah, it's like lagging a lot. Alright, anyways, I'm gonna go ahead with this. So let's do if something is no. Let's do if something is not no. If it's no, we just kind of skip over it. Yikes. Left. So we want to check if node.left's value node.left's value. We also need to check if lower and upper are set or not.
So what does check node do? Can you tell me what it does?
Takes the left and right ones and so it either checks two things. It checks if the node itself. Yeah, so I think what I had before was a little bit better with the check node left and right. So basically it takes the node itself, check if it's no. If it's no, then you just return it to true. Otherwise, if it's not, you check if the lower and upper bounds are no and see if it fits this condition for the lower and upper bounds. But yeah, I think it's cleaner if I pass it in to the same function.
So what are you doing when you call recursion check on the left and right
here? We're recursing the children of it. So the check node can check its children.
Hmm.
Basically, I can implement everything here for the checking of the node itself.
So when you given a node, how uh
So let's say if are you concerned about the case where I am given only one head node and have no children?
no, so I think this can be a lot simpler. So first, let's look at node itself. Let's ignore the children for now. What are the conditions for it to be okay? Given, so you have node, you have lower, you have upper. What are the conditions for that node to be okay?
Check if the value itself is lower or upper. I guess like check if the value itself on the left is less than, on the right is greater than. So no, I think you're right. Yeah.
So let's say you're looking at in your actual example, you're looking at 7, right? And
Yep.
then
Yep.
I think at that point, so the lower bound would be 5 and the upper bound would be 10. So how do you make sure that node
Mhm.
is valid, the one at 7?
Yep. Yeah, I think I see what I'm doing wrong. Yeah, so I don't need to check for bounds here. Well, do I?
So after checking if that node is null, why don't you just ignore the children for now? What do you have to do to make sure to see if that node is valid?
Um,
Within the lower bound and upper bound.
right. If the value is, well, less than upper. It's frozen. And oh, so you check this case.
Mm-hmm.
I need to break it apart because lower and upper can be null as well. So
Is it lagging?
yeah, it's lagging really badly. Nope. Do you want to switch platforms?
Okay.
Or
Sure.
let me just type it in Sublime. and you can just look at my screen. Okay. Or actually Adam. Oh god, this is so bad. What? Sorry, give me a second. Not sure how to.
Or just save it as something .java.
That's a good point. Okay, yeah, there you go. Yeah, so essentially, I guess what I'm doing here was what I was trying to do here. I know you say there's... Oh god, the tab is 2. Okay, I'm just gonna do one long if function. Let's do... lower.
So what are you checking for?
I'm checking the node validity of it.
You're checking whether it's valid, right? Whether the value falls between the lower and upper bounds. And you're also checking whether lower and upper are valid. So,
Yep.
so if lower is null, what does that mean?
Then the value can be as low as it gets. Did you stop me for a reason when I was doing this?
This part?
Yeah, the check node part.
Well, I wasn't sure if you were doing another recursion.
No, I wasn't. I was just checking it.
Okay. Yeah, I wasn't really following, but okay.
Okay.
So
Um, I think I like screwed myself in a corner. So here. Okay. Okay. If left is equal to null, so yeah, so this node, it would just be node. We don't care about that. Let's do if lower is not equal to null, then the node needs to be greater than lower. So put that in here. Else, if it is null, just return true. I could condense that later. Developer. I think that should work.
So, normally I would ask you to step through check node to see, to make sure if it works. But since we're
Mm-hmm.
spent a lot of time already, I'm just gonna say, the lower. So the conditions here. So if lower not equal to null and node dot value greater than lower, like um, you're saying. Okay, so okay, first of all, I think you meant so I you're setting
Yep.
lower and upper check both to true no matter what.
Yep.
So it's not equal to null. Okay, that's fine. And let me look at this. Okay. Uh, so why don't you walk me through recursion check?
Okay. Um, So I'll just start with a small example.
Mhm.
I guess we'll do this one. Once I pass in the 10, notice 10 is not null. And now we check the node. So 10, no here.
Okay.
This will be lower check is true, upper check is true, so this will return true, it's valid. And then we recurse. So for 10, I guess it's valid.
Mhm.
Now we recurse the left. Left would be 5. Lower would be let's just lower, which is still null. Here. Node value would be 10 for upper. So when we're doing the check node within the 5 itself, so lower is still null, upper is now 10, so it's not null. And then we can do value, which is 5, is less than upper, which is correct. So this will return true. And then we check 1. And that should work out as well. So I want to do a case where it's like where you both have upper and lowers. So let's say this 7 here. Once we've done with the 1, we will actually pass in 7. So for this one. So the second recursion check for the 5. This will be the 1. So we pass in. So the second recursion check for 5. They'll pass in 7 here. 7. No dot value, which is 5. And the upper takes 5's upper, which is 10. And when we do a check node on 7, lower is not equal to null, is 5. Value is greater than lower, 7 is greater than 5. Lower is not equal to null, value is less than 10, so 7 is less than 10, so that's true. So this will return true. And if 7 has no children, when they're passed in here, this will both return true. So honestly, I guess like this is valid needs to check this. If left tree is valid. Yeah. I think that will wrap it up for this equation.
What happens if it's not valid? Let's say, what happens if...
Yeah, sorry. I feel like this is a little bit overkill. Like, I could have done something shorter.
Yeah.
Yeah.
So for now, I mean, I don't know if I don't know if there are any edge cases where it doesn't work,
Mm-hmm.
it seems to work, or at least um, to the extent that I can follow it, it seems to work. So I'm gonna say we
Mm-hmm.
stop now.
Yep.
So let's the time. So I know you had some technical difficulties just now, but so my timer says we spent 62 minutes,
Okay.
which so yeah. Let's see.
So I could have
Can
done a simpler check somewhere here, I think.
So yeah, I'm gonna tell. So I'll let you know where you can look at the solution later, and I think you should definitely look at the solution. And but
Yeah.
yeah. So first, uh, so for the binary search tree, one condition that you missed was uh, whether duplicates are allowed. So
Uh-huh.
yeah, but that's not really any. Well, that's just an observation, and so it's good that you started with an example. I think in this case, not in every case, but in this case, if you had made a counter example, that might have helped a bit, but then I'm not
Mm-hmm.
sure.
Okay.
Um, so one thing, when I asked this question, I wanted to uh, hear you talk about how if you do an in-order traversal, if there aren't any repeated elements, you can essentially do an in-order traversal,
Mm-hmm.
and if each element, if it's in order, if each element is greater than the one before it, then essentially it is a binary search tree.
Mm-hmm.
But I think I didn't hear you mention that. So
If it's
yeah, that
greater
was
than
one.
the one before it.
So,
So
I
you
mean,
mean, do we pass in reference of the value itself to the next?
so essentially, I wanted to hear you, you know,
Just say it.
talk about, or at least like think about doing an order traversal. But uh, yeah, but
Mm-hmm.
yeah. Anyway,
Okay.
so I wanted you to come to that conclusion, but I think you might have missed that.
Mm-hmm.
And then so also, uh, so actually, let's see this. Um, it's good that you caught some of your mistakes when you were going through you were working through the examples. So it's good that I didn't have to um, point them out to you. So
Mm-hmm.
that's okay. I think uh, the most important thing for you to do is to spend more time on recursion, as
Mm-hmm.
I think I don't feel that you're too comfortable with
Yeah,
this.
I still don't like it.
Yeah. So I think you should spend more time on it. Go
Mm-hmm.
through a few examples in the book, if not all of them. And so this question is actually question 4.5
Okay.
in the book. So yes, please go through the solution.
Mm-hmm.
Yeah, that's it.
Okay. All right. Well, thanks for joining
Definitely,
us today.
oh, yeah. Thanks for joining us.
I'll see you guys later.